Okay, so how many outfits? So I asked you to do the little warm up, and I didn't want anything spectacular. I just wanted you guys to write down by putting stuff together, because it did tell you how much of each you needed, right? So this one, we're going on a trip, right? San Diego, and this person packed 2 t-shirts, one of each, one black, one white, packed 2 pairs of shorts, one red, one gray, and then packed 2 pairs of sandals, so one black, one brown. List all the different outfits that are possible with those scenarios. So assuming that you had to have a pair of shorts on, have a shirt on, and a pair of sandals, okay? So did you guys get 8 different outfits? Okay, so again, this question, can you guys visualize how you can get all the different possible outfits? Yes, because there's not that many options for the outfits, okay? But do you guys see how this could be a really big problem? Yes. So there obviously has to be an easier way to figure out how many possibilities for outfits there are. So is there an easier way to determine the number of possible outfits without listing all the possibilities or drawing a tree diagram? Did anybody draw a tree diagram to do this? Right? Could that have worked? You could do whatever. Because it says list all the different outfits. So remember when we did our probability, we did a few different things when we just did our outcomes. We did tree diagrams, okay? This one I just listed them. I just started, okay? Doing my t-shirts first, so I did all the scenarios where I had black t-shirts. Okay, so I used logic to do this, right? And just listed them all, but would a tree diagram organize this very clearly? You just would have had 3 levels. Do you guys picture the levels? Right, the first level would have been a B and a W, and then 2 branches would have went off of there, right? And then both those branches would have been a R and a G, and then 2 more branches off of each one of those, okay? So what it could have, like I said, you could have did a tree diagram to organize it well. You didn't have to, okay? So there is 8 possible outcomes. So how many choices for shirts did you have? 2. How many choices for shorts did you have? And then how many choices for sandals did you have? So what can we do with those choices to get out 8 outcomes? Did anybody make that connection? Yeah. Multiply them together. So if you didn't make that connection, that's okay. But this technically, guys, is what we call the fundamental counting principle. Because in this chapter, we're going to be asked to figure out how many different arrangements can we do. Okay? In this one, how many different outfits can we make? And it is not realistic, guys, for you to do sample spaces. Okay, I wanted to do one where I can do a sample space. I'll do it just to show you guys the visual, just because otherwise you have to just trust that the math is working. That's why students like this chapter, because it's interesting. Okay, it's very cool, it's kind of neat. But the reason why some students don't particularly like the chapter is you can't check. You have to just trust the formulas. Okay, because do you think if I change this to, just think about it, if I had 5 shirt options, 4 short options, and 3 sandal options, is my sample space now way bigger? Are you going to actually make all those outfits? You're going to write all the outfits down? No. Well, you can't, because sometimes your options are going to be like 550,000. Okay. You're never going to finish the test. So this one, you won't be able to, because like I said, some are going to be in the millions, okay? So if you want to try, you can at least maybe do a pattern to see, like, make you feel better about it. But that's the piece, guys. With this chapter, we're using formulas. You can't technically, like sequences in series, a lot of times students kind of just add the whole sequence together instead of using the sum formula, right? Here it's a little bit harder to do. Right? So it's kind of a love-hate sort of thing, because I know people in this class like to check things 8 different ways. So is that a bad thing? No, absolutely not. I'd rather you over-check stuff. But with this chapter, it's hard to check. Okay? You have to just make sure that you get all your restrictions very clear in your head, because that's what we're going to do, is I'm going to keep adding restrictions to you guys. Okay, which makes no sense right now, but it will by the time we're done the lesson. is we're going to maybe make outfits, but we might be arranging letters. Okay, how many different ways we can arrange different words. How many ways we can line up to a water fountain if there's 7 of us. So that's kind of the permutation part of it. Okay, so the chapter is permutations and combinations. So permutations, you have to think about arrangements. Okay, how many ways can we arrange things, whether it be letters, here arrange outfits, okay, so those sorts of things. So that's kind of where we're headed in this chapter. Combinations is more grouping, but we'll talk about that later. Right, so that's what this is saying. So the fundamental counting principle, if one task can be performed in A ways and a second task can be performed in B ways, then the 2 tasks can be performed in A times B ways. Okay, so again, if we're making an outfit, if there's 2 shirts we can pick, right, and 2 different shorts we can pick, and 2 different sets of shoes we can pick, how many outfits are possible to put those together would be A times B times C in this situation, where A is representing shirts, B is representing shorts, and C is representing our sandals. That's a fast way to get how many arrangements or outfits in this case we can get. Okay. So again, I know it sounds confusing, but I promise you it's kind of a really neat chapter. Okay. All right, so let's look at some examples. So example 1 says a 30-1 quiz consists of 5 multiple choice questions. Each question has 4 choices, A, B, C, or D. How many different sets of answers are possible? Okay, so how many multiple choice questions are there? 5. So we have 1, 2, 3, 4, 5. Okay, does that make sense why I'm doing that? Those are blanks. I don't have to actually go make little 5 lines, but this is what I like to do to organize my information. Because if we're picturing fundamental counting principle, okay, the task is answering each multiple choice question. Do you guys agree? So how many different choices do I have for question A? 4. How many choices do I have for question B? 4. And so on. So do I have 4 choices for every single question? And what do I do with all of them? Multiply them. Right? So if you made that connection very quickly, you could have just said this would be 4 to the power of 5. So 4 to the power of 5 is there's 1,024 different ways you could bubble that sheet in if you're bubbling your answers in. Okay, exactly. So again, so does that make sense how you could guess and get 100%? So could we change this to a probability question? We could in IB. Okay, but do we have any probability in 30-1? No. So we just stick, this is where we stop. Okay, but if we wanted to, just to kind of show you guys, whoopsie. Right, so the chances of you guessing or getting 100% is not even a 0.1%, okay, that you would just randomly guess all the right answers. Because does that make sense why I took the second one and times it by 100? Because remember, probability is not percent yet. You have to times it by 100. So there's a basically 0.1 if we round it to the nearest 100, 0.1% that you could get, just randomly bubble in the correct sequence of A, B, C, or D. Okay, so kind of neat. All right, so again, would you want to write down all the possible arrangements of how you could bubble it in? No, because there's 1,024 A, B, C, D, right? Versus B, C, you know what I'm saying, like yuck. Okay, all right, so kind of neat. So here it says an online game has asked you to create a password. The password must be 4 letters in length, and you may use lowercase letters and uppercase letters and any single digit to create your password. So how many passwords are possible if you repeat any characters? Because does it make sense that I have to tell you whether you can repeat or not? Because if you can repeat, you have more options, right? If you can't repeat, that makes you have less options. So again, how long is this password? 4 characters. All right, so once we talk about this, hopefully you already know, okay, but how many letters are in the alphabet? 26. So a lowercase, A to Z, there's 26. Uppercase, is there the same amount? Yes. So we're just trying to figure out how many choices I have. And then we have digits, so 0 to 9. So how many digits from 0 to 9? 10, good. Right, so then how many options in total do I have? So 26 plus 26 is 50. 2 plus 10 is 62 options. Right, so I have 62 choices. When I look at my first option to make my password, I have 62. How many for the second part of my code, or my password, sorry? 62, because can I repeat? Yes. So technically, could I use uppercase A, uppercase A, uppercase A, uppercase A? Would that be smart to use uppercase A, uppercase A, uppercase A, uppercase A? No.
That's why I use WordPass as the password. That's a good one.
Well, you just should change your passwords quite often. Yeah. Well, and the thing is, guys, that's why anytime you're asked to make a password now, doesn't it give you restrictions? Guess what we're headed to? Restrictions, right? Where it might, not necessarily with passwords, but just restrictions in general. Like you might have to use, because normally with passwords now you have to go to all like apostrophes or stars and stuff like that, right? So they don't usually use symbols here because they don't expect you to know how many different symbols are on a keyboard. But we will do restrictions. Like it might have to start with a capital P, right? So if I changed this, but the only thing I changed to was it had to start with a capital P, the first 62 would now become a 1. That would be the change. Okay? Which makes sense. Does it make sense that we're going to have less options if we put restrictions on? Yes. Okay? But if we add more letters or symbols, right, that creates more. But that's kind of where we're headed. We're going to start adding restrictions. Okay, so if there's no restrictions, then this would be the same thing as 62 to the exponent of 4. So 14,776,336 different passwords you can create, which might seem like a lot,
It's actually not really secure.
but what cracks codes now? Robots, computers, right? So if you were doing this paper pencil, would you be there for a while? Yeah, that's not how hackers get into your stuff anymore. They have computer programs that can run through stuff super duper quick. Okay. All right, so then next one, it says how many passwords are possible if you're not permitted to repeat any character. So the only difference now is every single number, right? The 62 will be still 62. Will one of them still be 62? But then every single one after that will go down by 1, right? Because again, does it matter where I start here? No. If it doesn't matter where I start in my choices, I always just start on the left. Okay. Does it matter though? No. So if I choose my first part of my password first, I have 62 choices. If I choose the second part of my password as the next one right beside it, I have 61, because only one can't repeat. So if I chose a lowercase p for the first one, that's now gone. I can't pick it. So now I have 61, and then 60, and then 59. How is that sitting with everybody? Does it make sense it goes down by 1, not by 4? Because I'm only leaving only one letter or number can be in each spot. So then 62 times 61 times 60 times 59. So now there would be 13,388,280 different passwords I could create if I could pick from uppercase, lowercase letters, and single digits. All right. So passwords are kind of neat. Could I add so many more restrictions with passwords? I could. We do passwords, not a ton of restrictions. Passwords, it might be like it has to be 3 letters by 4 digits. Okay. So, and you guys will see as we go through examples. The main one that you the world we live in is arranging words. Okay, which is kind of fun, but you have to understand though, guys, if I asked you to arrange a word with different restrictions, you have to think you just have those letters. You don't have, unless it says letters can be repeated, you always assume if you're arranging a word, they're Scrabble tiles. So in this situation, unless they say I can repeat, you have how many E's? You have one E. You have one N. You have one G. You have one L, one I, one S, one H. So anytime, like I said, they give you a word, think those are the tiles you have. That's it. Unless in the question they say you have no restrictions. They say that letters can repeat. Because here it's an automatic restriction. Those are the letters you have, no more, no less. Okay? Unless in the sentence they say you have unlimited E's. Then you change it. Right? Then you couldn't, because there's only, you'll see what I mean when we do the question. Like if you can repeat letters, is what I'm saying. So here, determine the number of distinguishable four-letter arrangement that can be formed from the letters in the word English if there's no restrictions. So again, even though there's no restrictions, how many E's do you have? One. How many N's do you have? One. So if there's no restrictions, you have to assume, okay, you can't repeat any because you only have one E. Okay, so you can't repeat the E because you only have one of them. Okay. All right, so how many letters in the word English? 1, 2, 3, 4, 5, 6, 7. All right, since there's no restrictions, does it matter where I start? No, because can I pick to put a letter anywhere in that arrangement? Yes, so again, guess where I'm going to start? I'm just going to start on the left and make my way right. If I don't have restrictions, that's just my OCD going, I just want to do the same thing every time. Okay? Because does it make sense, guys, that it doesn't matter, though? Because what operation are we doing? We're doing multiplication. So if I move stuff around over here, are we still getting the same number? Yes. Yep. Good question. We'll talk about that. Okay, so let's do this one first. So if I'm arranging all of them, I start on the left. How many choices do I have to go in the first position? I still have 7. Do you guys agree? Oh, never mind. I should read the question properly. So yes, so 4-letter arrangements. So do I have to erase some of those? Yeah, the last 3 I have to erase. Yeah, you guys aren't losing it, I am. Okay? Thank you. Nope, I just need to read. Yep. So we're only making 4-letter arrangements, so cut off the last 3. So, but now the process is the same. So how many choices do I have to put in the very beginning of my arrangement? 7. So how many choices do I have for the second spot? 6. Third spot? 5. And fourth spot? 4. Right? If I arranged all of them, would I go all the way down? Yes. So thank you, Jamie. Right, so then 7 times 6 times 5 times 4. We are also going to learn different ways that this can be written. So right now, today, we're going to focus on this first part, fundamental counting principle. So just showing what we're multiplying. So this will equal 840. Right, so this next one, first letter must be an E. So we're still doing a 4-letter arrangement. So 1, 2, 3, 4. But if the first one has to be an E, deal with the restrictions first. Okay, so how many choices do I have for the first letter? 1. Because it has to be an E, so I only have 1 choice to put there. And then, how many choices do I have for the remaining? Doesn't matter where I start, I'm just going to start left and make my way right. So second spot, how many letters do I have now? 6 times 5 times 4. So that's 30 times 4, so 120. Different 4-letter arrangements we can make starting with an E. All right, so the arrangement must contain an H. What are we going to do with that? So same thing as B? Is it exactly the same thing as B? No, because we will do what we did in B, but we'll have to times it by. Nobody? So how is B and C exactly the same? So, yes. You will have to times it by 4, because the difference is, guys, this one, the E has to be where? The first one. Does this H scenario have to be the first one? No. So is there 4 different places the H can go? Yes. So either you do one case and times it by 4, or do you have to do 4 cases? Because the H can be first, it can be second, it can be third, it can be fourth. Hannah, is that making sense? Because your face is like, what? Is that making sense now? So you have to, again, E has to be first. It does not say H has to be first. So I'm going to write all the cases, because then none of you should be lost. Because the H could be there. The H could be here. The H could be here. See why, though, if there's like a 10 arrangements, this would suck doing all the cases. So you make because is each case going to multiply to the same number? Yes. So if you notice, right, each case is the same. You can do one case and times it by how many spots there are. So if H is first, then it's going to look exactly like B. Right? If the H is second, is it still going to multiply to the same thing? Yes. If H is third, it's still going to multiply to the same thing. And H is fourth, because the arrangements of the numbers that you're multiplying, guys, ends up being 6 times 5, which is 30, times 4, which is 120. But we do need to times that by 4. Or do each case and do what with all the cases? Add them together. So 480. So order does matter, guys. So if they don't tell you a specific position, you have to do all the cases. Okay? Does that make sense now, the difference between B and C? You all see that? Okay. So then the first and last letter must be vowels. So assume Y is not a vowel unless it tells you Y is a vowel. Okay, so we do need to know, they do expect you guys to know what your vowels are. Okay, so if you don't, write them down and memorize them. So our vowels, so not just in the word English, just write them all down and then we'll deal with the word English. So what's my first vowel in the alphabet? A. What's my next one? Next one. Next one. And perfect. Okay. So sometimes Y. So we do not use Y as a vowel unless it tells you Y is being included as a vowel. I don't think I've ever seen them included as a vowel, but I don't want to say never in 30-1. But you assume never unless they tell you in the problem that it's being included. But those are always the vowels. Okay. So then we are going back to the word English. So are we going to have to worry about all of them? No, we're just dealing with, in this situation, we're only dealing with the E and the I. So those are the only two we have to worry about in that word. So then we have 1, 2, 3, 4, 5, 6, 7. So we do have to deal with the restrictions first. So the vowels have to be the first and last. So it's your choice. Do you want to deal with the beginning or the end first? Because it doesn't matter. Oh, I did that again. Goodness gracious. I don't know what's going on today. There we go. So the next part's the same. Do we want to start at the beginning or the end? Because that doesn't matter. Beginning. So if you start at the beginning, how many choices do you have? 2. Right? So does it make sense that if you started at the end, it would still be 2? The ends are going to be a 2 and a 1, no matter what. So it's your choice. Doesn't matter. You just have to start there first. So vowels first. Now those are gone. So how many choices do we have for the next two? And again, order here doesn't matter. So 5 and, because we started with 7, so the two vowels are out now, so we have left is 5. So then that will be a total of 40 different arrangements we can make from the word English. And again, remember guys, these arrangements do not mean we're making words that make sense. They're just arrangements of letters. Okay? Probably can't make any other words that make sense out of the word English, but maybe we could. We're not doing, does that make sense though, guys? We're just arranging letters, not to make actual words. Okay? So there's 40 different arrangements we can make using the letters in the word English, where it has to start and end with a vowel. Okay? Pardon? Because, so are all of you guys thinking I should times this by 2? No, there's not 2 options here. The only way there'd be 2 options here if you did it this way. If the first one starts with a E and the last one starts with a I. Then the other case would be start with an I and end with a E. Now there's 2 cases. But since I did, the first one is an E or an I. Does it take care of both? Yes. So here I don't have to do 2 cases because I'm saying the first can be an E or an I. So it takes care of both. So if it's an E, the last one's an I. If the first one's an I, the last one's a E. So it takes care of both cases there. Does that clear that up? Okay, so if you did do both cases, like I said, you'd have to separate them. E, I, E. And then it would be 20 and 20, which still adds to 40. Pardon? Oh, yeah, no. If you just went 2 times 5 times 4, no, you wouldn't lose marks. Nope, nope, nope. Because on a diploma, they would never say times 1 at the end. I'm just putting it so you guys can see everything, okay? So you wouldn't lose marks with leaving the times 1s out. All right, so example 4 says, in how many ways can a teacher seat 4 girls and 3 boys in a row of 7 seats if a boy must be seated at each end of the row? All right, so I'm going to write this down properly now. This one has 7. Holy moly, it's been a day already, and it's only Monday. 2, 4, 6. Oh, that's really long. So 2, 4, 6, 7. So this must be a boy. So again, as soon as there's restrictions, deal with the restrictions. Okay. So boys have to be on the end. So if we start on the far left, how many boys am I looking at that I can sit at the beginning of the row? Right, so again, good. So we have 4 girls, 3 boys. So if I'm looking out and I'm grabbing them to sit, as Kaya said, I have 3 choices to choose to put here. Okay, so then I sit him there. How many choices do I have at the end? 2. Now, I don't have any other restrictions. Okay, because could I still have a boy-boy? Could I have a boy-girl? Yes. So no other restrictions, so the rest of them are just staring at me and I can pick any of them. Okay, so how many choices? Because it doesn't matter where I sit them now, okay, because it's multiplication. So how many students do I have still left to sit? Right, because I had a total of 7. I took 2 away. So I have 5 choices. It could be boy, it could be a different girl. Again, doesn't matter. That's the thing. When we're doing this, you don't get to see all the arrangements. You're just trusting. Okay? So then next one I have 4 and 3 and 2 and 1. So 3 times 5 times 4 times 3 times 2 times 1 times 2. So there's 720 different ways I can arrange a row of 7 starting with a boy at the beginning, a boy at the end, okay, and having to begin with 3 boys and 4 girls. All right. So the next thing I'm going to introduce to you guys is just notation. Okay, so this next little piece, because some of you have asked about this already, have you guys seen this symbol in math before? Right? So that symbol in math is called a factorial. Okay, so we can use it in the permutation section, okay, or in this chapter. And what the factorial symbol means is if you write, say, 5 factorial, that's a fast way of saying exactly 5 times, 4 times, 3 times, 2 times, 1. So does it actually come in handy? Yeah, because if you have 10 times, 9 times, 8 times, 7 times, 6 times, 5 times, 4 times, 3 times, 2 times 1, isn't it way just nicer to go 10 factorial? Yes. So factorial does go all the way down to 1, okay, when you're dealing with an actual number, okay? So when you see that symbol, that's what it means. If you're writing something out, like this one, could have I used actual factorial in this one? Yeah, I could have said this was the same as 3 times 2 times 5 factorial. Okay, I could have wrote it that way. And you need to be prepared on the diploma or on your quizzes, which I will get up there. It's not up there yet. They might write things in different ways that mean it's the same thing, which do I always tell you every single way we can write stuff? So this will be another chapter where there's equivalent ways to say the same thing. So factorial will be one of those things that can help you write things that mean the same thing as all the way down to 1. Okay. Yep, well, I'll show you. Okay. So then here, how many ways can 5 children line up at a water fountain? So with this one, if we're lining them up, can you guys see that this would just be 5 factorial? Right? So if you see this right away, because again, when you're lining 5 children up, when you're looking at all the little guys and girls, right? No restrictions on boy, girl. We know that I have 5 choices. Who gets to line up right gets to go first. Okay? Then I only have 4 choices for the second person, 3, 2, and 1. So this would be the same as 5 factorial. So on your calculator, okay. So if we go into 5, then you're going to hit math, and then over to probability. Okay. So this will be kind of the screen we kind of play in. So we will use number 2, we'll use number 3, and we'll use number 4. Okay. So again, to find this, we hit math, over to probability, and then number 4. That's where you find your factorial symbol. So just hit number 4, hit enter, and it just does that math for you. So the next thing, does it make sense that we're going to use factorials to help us simplify? Okay. So right now, do you guys agree that without simplifying anything, that this would be very unfair for me to ask you to go 10 factorial divided by 8 factorial and not use your calculator? Right? Without simplifying. I don't expect you guys all to go 10 times 9 times 8 all the way down to 1, get that number, and then divide it by 8 times 7 times 6 all the way down to 1, and then simplify. But I do expect you guys now to be able to use the idea of factorial. Okay, so watch what I mean by that. Do not write this down. So don't write this down. I want to show you guys something. So do you guys agree that this is equivalent? Can I divide that out with this? Can those just disappear to a 1? So can you guys all go 10 times 9 in your head? What is 10 times 9? Right? 90. So I don't want you guys to expand it like that. I do it this first time just to show you guys But technically, can I just do this? 10 times 9 and stop where the bottom is? Can I stop my factorial? The factorial will disappear with numbers if you go all the way down to 1. Do you guys agree? But can I stop it? Yeah, so just stop it where the bottom is. Just saves you some writing. Because you can stop a factorial at any part, okay? It's just in the top part, the factorial can disappear because I finished it. Here, I can, 8 factorial divided by 8 factorial is gone. So this still equals 19, okay? And the reason why I want to show that is if I gave you guys something like this, 99 factorial divided by 97 factorial, do you guys want to go all the way down to 1? No, okay? This would be the same thing as 99 factorial, or sorry, 99 times 98 times 7, and I would stop. This one I'd still use the calculator because I don't want you guys to do that. But isn't that way nicer than going all the way down to 1? Yeah, we would never do that, okay? So then you could now calculate that on your calculator. Okay. So we will simplify expressions that have numbers in it with factorials, which are nice. So this little guy here, I'm going to go all the way down to what? 7 times 6, exactly. We'll go down to the 4. And again, we didn't stop it at the 1, so it still has a factorial on it. Okay, it doesn't get rid of the factorial unless we get down to a 1 with a number. So this is still factorial 4. So then the 4's divide out. So here 6 times 5 is, this is how I would do this one in my head. 6 times 5 is 30. Just think, 3 times 7 is 21, add a 0. So 210. And you're done. Okay. All right, last thing I want to do with you guys is, does it make sense that we're going to variables? Yeah, only makes sense that we'll do the same thing. So you have to understand, guys, when I put a factorial on it, from one term to the next, we're going down by what? 1. So if I start with an n, what's the next term? N minus 1. What's the next term? N minus 2. What's the next term? So will we ever get rid of the factorial when I'm just following that pattern? No, I can't. Because am I ever like, will it ever stop? No, but you will stop it once you hit the bottom, or technically could I want to try to reach the top? Yes, depending on which one's bigger to begin with. So here you guys have to look at this and go, okay, I have to subtract 1. So am I expanding the top or am I expanding the bottom? The top. Because if I expand the bottom, guys, what's the next one? N minus 4. The next one is n minus 5. Is the bottom ever going to get to the top? No. Okay. So I have to expand the top. So we start on the piece that it's at. So if I expand the top, the first one is a what? N. The second one is a n minus 1. The third one is an n minus 2. And the fourth one is an n minus 3. Now I stop. So you're trying to get what's on the bottom. And it still has a factorial on it, which is beautiful, because does the bottom have a factorial on it? Yes. So the factorials will divide out along with the n minus 3's. So then this would be the same as n times n minus 1, n minus 2. Since there's only 3 things being multiplied, they would probably expect you to expand that. So minus 1 minus 2 is minus 3n in the middle, plus 2. So I just expanded the n minus 1, n minus 2's, which then is an n cubed minus 3n squared plus 2n. If you find yourself in a situation where there's more than 3 things you're multiplying, I don't expect you to expand it, but more so I would look, did you do it properly? Something else should divide out. Okay. Did that make sense what I did there? So I did put the minus 1n and the minus 2n together. I didn't you guys should be good with that by now, right? Good. Right, so that simplifies to that, right? Lots of simplifying. Right, so then this little guy here, am I going to expand the top or am I going to expand the bottom? Right, so if I expand the bottom, I'm going to have an n plus 2. The next one's going to be an n plus 1. The next one's going to be a n. So does expanding the bottom make sense? Think about it this way, guys. You're always expanding the bigger one. Because can you make the bigger one become smaller? Yes. So think about which one's actually bigger. Because bigger, we know that when we're dealing with factorial, we're going down. You guys agree? So I have to expand the bigger one. So n plus 4 is bigger than an n plus 2. That one I can expand to make it look like the bottom. Whoopsie. So I'm starting with an n plus 4. Subtract 1, and now at an n plus 3, n plus 2, boom, bang, got the bottom. They divide out. So then I'm left with an n squared plus 4n plus 3n is a plus 7n plus 12. And we're done. So not that we really talked about it yet, guys, but do we have restrictions here? What can we not take the factorial of? Negatives. We'll talk about 0 later because we can actually take the factorial of 0, but we're not going to talk about that today. So are we all definitely confident that we cannot take the factorial of a negative number? Yes. And the other thing is, do they have to be wholes? Yeah, because they're objects. It's a number of something. So you can't find, 2.5 n's. Doesn't exist. They're all whole number objects. Because we're counting. Nope, can't have it. Okay. All right. So with that, we aren't going to deal with 0 today. So I usually break this up into 2. So that is enough for today. So what I want you guys to do is I think I have your textbook split up into 2.